When we plug in our radius's length, we get 2 times pi times 12. Now, maybe in your previous classes you would have replaced pi with 3.14, okay? Maybe in your previous classes you replaced 3.14 for pi. We're never going to do that again. Never, never, ever, never, never going to do that again. When you're dealing with circles or cylinders or spheres, you're going to have an exact answer that will be in terms of pi, which means pi will be in your final answer. Be in your final answer. So right now we're multiplying these three values. We have 2 times pi times 12. We can simplify this. Rather than having 2 times 12, we can just compute that. That is 24, and then we have pi. This is an exact answer. I have done no rounding. I haven't replaced pi with some rounded decimal answer. This is exactly, the circumference is exactly 24 times pi. Pi is an irrational number, meaning you can't represent it as a fraction. It goes on forever and ever and ever. The decimal never stops. It keeps going on forever and ever and ever. So, if we needed a rounded answer, we're going to go to our handy-dandy calculators for that. We will never plug in 3.14 for pi and then type, oh, what's 24 times 3.14? That's never going to happen again. If you look at your calculator, the button below clear. The button below clear. That button looks like a little hat, little carrot thing. Okay? Its secondary function is pi. Its secondary function, written in blue ink, is this irrational constant, pi. So, if I hit the blue second button on these calculators, and then I hit that carrot top button right below clear, then on your calculator you should see the symbol for pi. If you hit enter, the calculator will give you a rounded answer for it, and it's 3.141592654. We're going to use that symbol every single time we get a rounded answer for circumference, area of a circle, or if you're looking at cylinders or spheres, whatever. If I need a rounded answer, you will type this symbol into your calculator. So I have 24, I'm going to type 24 in my calculator, and then multiply that to the pi symbol. We are not going to be using 3.14. Then the calculator spits out as a rounded answer, and I'm going to keep the same notation. I got the wavy equal sign, because this is an estimation, this is a rounded answer, this is no longer exact. 75 point. Now we're going to round to the nearest hundredth. We're going to round to the nearest hundredth. So that means 2 decimal places. 2 decimal places. Right now it reads 39.8. So this is what your calculator reads. It has other values as well. It says, 2, so on and so forth, blah, blah, blah. But if I ask you to round to the nearest hundredth, that means 2 decimal places. So, right now, this decimal, we have 39 hundredths. That's how many we have. We have 39 hundredths. We have 3 tenths, 39 hundredths. We have 398 thousandths, so on and so forth. So if we're rounding to the nearest hundredth, right now we got 39. We look at this number over here, it's an 8. So what does that mean? It goes up to what? 40. Okay, it's going to go up to 40. So now, when we round this correctly, this is 75.40. If I ask you to round to the nearest hundredth, that's 2 decimal places, you must represent that place value. You must represent that place value. And again, I'm going to keep the same notation. I got my wavy equal sign because it's an estimation, it's not an exact, and I'm going to circle my rounded answer. Okay? My exact answer is in a box, rigid. It is exactly that. And my rounded answer is about 75.40 meters, and we circled that. I want you to do the same thing for the area of this made-up example. Area of a circle, it's on your formula chart, but you probably should have this just memorized. Pi r squared. I want you to give me the exact answer and the rounded answer for the area. Sweet. For the area, what is my exact answer?
144 pi.
144 pi. Keep going. Keep going. Keep going. Meters squared. Area is in square units. It's a surface. It's 2 dimensions. My rounded answer, however, Harley, please.
452.4 L.
452.40.
40. Yes.
Does everyone agree? Okay. This is what your calculator should read. It's got more. So we're around to the nearest hundredth. Right now I've got 38 of them. And so when we round, we look to the next number, it's a 9, so it's going to go up to 39 meters squared. Okay. Fantastic. The reason I bring that up is because on the workbook pages, let's go back to that page we were just working on. So 229. On page 229, I want you to do number 7. We're finding the total surface area. I don't care what the directions say. I don't care what the directions say. We're going to look at that cylinder, and we're going to find the total surface area. But now, I want you to give me an exact answer, then around it. Number 7. All right, looking at number 7. We've got the radius is 5 and the height is 15. When you're finding the total surface area of a cylinder, that's the only 2 things you need, is the radius. And the radius of the base is the radius of the entire cylinder. And so the formula should say, we got 2 pi r times the height plus 2 pi r squared. Is that correct?
Yeah.
Wonderful. That's what it should say on your formula chart. So just plug in what we had. Our radius was 5, our height was 15. If I make a mistake, please stop me. Plugged in everything correctly? Okay. So we've got that the total surface area, we need to simplify this. I have 2 times pi times 5 times 15. We're just going to multiply those coefficients. So 2 times 5 is 10. 10 times 15 is 150. And I still need to multiply that pi. So we're just going to write it right there. Just like we were like to 7x. We know that when we read 7x, we know that the mathematical operation that's happening is multiplication between that 7 and that. Okay, and then we've got 2 times pi times 25. Keep on simplifying. And I've got 50 pi is 2 times 25. 50. And now I can add these. I've got 50 of these things, pi's, plus 50 more. So these are like terms. We can combine these. And so my final answer would be 200 pi. I'm looking for the units. Centimeters was what they gave us. Those are the lengths of the radius and the height. So for a total surface area, what's my unit? Centimeters squared. Wonderful. Wonderful, wonderful. Okay, I would like for you to get out you should have already gotten out the circle notes and that other workbook page. The workbook pages, sorry, Quill. Oh, sorry, the workbook pages were 189 all the way to 204, and we've been looking and dealing with those circle notes for a good long while. We are discussing three scenarios. Three different scenarios in the back of you. One involves two chords intersecting inside the triangle. Now inside the circle. Now we've seen this happen before when two chords are intersecting, but we've looked at the angle measurements and the intersected arcs. And we said that, well, if the vertex is inside, then that angle measurement is 1/2 the sum of those two intersected arcs. So we've dealt with this diagram, this type of situation before, but we were looking at the angle measurements and arc measurements. Now we're turning focus to looking at the lengths of these segments. So when this happens, when two chords intersect inside a circle, each chord is broken up into how many parts? 2 parts, okay? So there are 4 pieces in the end. This point of intersection creates these 4 pieces. And the proof right above this on your notes proves that when this happens, if I were to draw some auxiliary segments here, we can prove, or we're not going to do it right now, but we can prove that these two triangles are similar. I know that this angle is congruent to that angle. Why? Vertical angles are always congruent. Okay? Then, this angle in this triangle right here is congruent to that angle there. Can someone tell me why? What's up, Kyle?
Is it because they share the same arc?
They intercept the same arc. Good. So check it out. This guy right here is opening up to this intersected arc. Well, this guy is also opening up to that arc. So yes, those two angles are congruent because they intercept the same exact arc. We've proven that these triangles have 2 congruent angles. If that's the case, can we say anything about these 2 triangles? They're similar. By what theorem? Angle, angle, similarity. If 2 triangles are similar, their angles are congruent. So we've proven that their angles are congruent. But what's true about their sides? They're proportional. Good, Sam. They're proportional. So we can set up a proportion.